So next up, we have Jaeyeon Won. Jaeyeon is currently a third-year PhD student at MIT, where he's co-advised by Saman, Amarasinghe, and Joel Emer. He has a research interest in compiler optimization and domain-specific languages, with a key focus on optimizing sparse tensor computations. Jaeyeon, you can take it.
Where's the... Okay, hi, I'm Jaeyeon Won, and I'll talk about Wako, which is about how to optimize sparse tensor program. Sparse tensor arise naturally in many domains of science. They are not only used in physical simulations, but also used in deep learning and graph computations. Writing a sparse computation is difficult. The data must be stored in sparse data representation to reduce the memory. Additionally, sparsity can be leveraged to reduce computational cost by skipping unnecessary computation from the intersection. Furthermore, there can be multiple ways to implement these programs. One approach of parallelizing is to split the rows of the matrix, while another is to split the columns of the matrix. You can also split the non-zero values for the better load balancing. Several compiler projects have been developed to support sparse tensor computations, making it easier for programmers to exploit sparsity without writing them manually. Among them, TACO is a compiler that can generate efficient sparse tensor algebra with many different formats and schedules. Suppose we want to write sparse matrix dense vector multiplication with TACO. We can specify the desired algebra in tensor expression language as follows. In the format language, if we choose to store matrix A in COO format, TACO will generate C code that corresponds to this choice. We can then execute this generated code by providing the input sparse matrix. You can also choose a different format for A, such as CSR format, as you can see in the slide. In this case, TACO will generate sparse code with the CSR format, which may result in improved performance. Furthermore, if the user can choose nice schedule that transform loop in a better parallelism and locality, it can lead to even better performance. While previous studies have built a compiler mechanism that enables this cool code generation, a policy for choosing the best format and schedule is still not been designed. So the question is, how can we determine the optimal format and schedule for a specific sparsity pattern? This is a challenging problem because there's no single holistic program that is optimal for every problems. Even in the dense case, you need to apply different loop transformations, such as different loop tilings, tile sizes, depending on tensor shape. However, in sparse tensor program, it is much more harder because the performance is also affected by its sparsity pattern. Furthermore, it is critical in performance to choose a proper format because some formats can reduce the memory needed and makes it easier to exploit optimization. As an example, if you want non-zero parallelism, COO may be the best format you can choose. If you want row parallelism, CSR format will be your best choice. If you have a structure sparsity, you may want to store them in a dense block format. Therefore, you have to consider loop transformation with schedules and format at the same time. Now, given this sparsity pattern, how would you choose the best format and schedule among this enormous search space? So we propose Wako to efficiently search co-optimized format and schedule for a given sparsity pattern. We adopt a program auto-tuning approach in Wako, which consists of 3 components: search space, cost model, and search strategy. Our search space defines the choices of formats and schedule, and the cost model predicts the program runtime based on the sparsity pattern. Finally, our strategy searches for the optimal format and schedule by repeating multiple rounds of cost model evaluations until it converges to a local optimum. Let's talk about our search space first. I would like to point out some of limitations of existing approaches when defining a search space. First, many previous sparse autotuners had only considered either format or schedule, which can miss optimization opportunities. The comparison table shows different tuning spaces in different columns for the sparse matrix on the left. And it is evident that co-optimization, which considers both format and schedule, can result in a significant speed up for this sparsity pattern. Additionally, many sparse autotuners have used a limited search space. The comparison shows that prior work have only considered a handful of format choices in their format selection. Recent advances in sparse compilers allows us to explore a huge space of choices. So to address prior work's limitation, we developed a parameterized template that defines both format and schedules, which we call superschedule template. This superschedule template has two components, compute schedule and format schedule. Compute schedule defines the loop transformation, and format schedule will define which format you want to store it. First, by filling the parameters in compute schedules, this will transform the original loop into more optimized loop nest with a parallelism according to your compute schedule. Now, format schedule determines which format you want to store it. I won't go like all the details of like theory behind and format abstraction behind the format schedule, but similar to compute schedule, all you need to know is this parameterized template can express a lot of different formats that Taco compiler can support by just filling different parameters. Our parameterized space includes 1 million pairs of format and schedule combinations, and allowing us to co-optimize because we both consider format and schedule at the same time. Now, let's take a look at our cost model design. Our cost model needs to understand a coupled behavior between sparsity pattern and the format and schedule. To achieve this, we designed the cost model to take two inputs, sparsity pattern and superschedule. It then predicts the program runtime. For Wako, we used a deep learning-based cost model composed of 3 parts. The feature extractor to analyze the sparsity pattern, and secondly, program embedder to analyze the format and schedule, and finally, a fully connected layer to consider coupled behavior between these two inputs. Here, let's focus on the feature extractor for now. There are 2 main approaches for understanding sparsity pattern in previous sparse autotuners, human-crafted features and convolution neural network after downsampling. Human-crafted feature is basically a list of statistical feature of pattern designed by expert. While simple and effective, this approach can miss a lot of important details of the pattern. On the other hand, more recently, convolution after downsampling treats the sparsity pattern as an image and feeds it into a dense CNN. However, in order to feed them into a dense CNN, we need to resize the original arbitrary size image to a fixed size image. And downsampling during this resizing can result in significant information loss. So to avoid this, we use the submanifold sparse convolution to capture original sparsity pattern without any downsampling, achieving better performance in understanding the sparsity pattern. Then what is submanifold sparse convolution? Here, I'm showing you 2 images comparing regular convolution on the left and submanifold sparse convolution on the right. When the image is fed into a regular convolution on the left, you can see that non-zero sites tend to grow quickly. So you cannot feed sparsity pattern without downsampling because the computational cost quickly becomes expensive in conventional convolution. However, submanifold sparse convolution ensures that the output sparsity pattern remains the same as the input by only performing convolution when the filter center is at non-zero input. So we can keep the computational cost affordable with sparse convolution. This kind of sparse convolution has been widely used in computer vision community to understand 3D point clouds. However, when we just plug in popular sparse vision model for our case, you can see that information does not propagate across like far away non-zeros, even we apply multiple passes of convolution. So using popular sparse vision model will not capture the pattern unless all the non-zeros are close to each other in your sparsity pattern. In order to cover this weakness, we propose a new network architecture called Waconet to understand general sparsity pattern. First, we use submanifold sparse convolution to avoid downsampling. Second, to solve the distant non-zero issues, we place a lot of stride layers in the vision model. Third, because the stride convolution will create a lot of multi-resolutional spatial feature during the intermediate layer, we combine them to understand the pattern better. Now, let's find out how we implement the search strategy, which is our final component. Our goal is to find an optimal superschedule or optimal formatted schedule in the search space that minimizes the predicted runtime given an input sparsity pattern. We view this problem as a nearest neighbor search, which is widely used in database system and information retrieval. As you can see in this picture, nearest neighbor search is the algorithm that searches a point which is closest to a query in terms of minimizing the distance function. Interestingly, the problem structure of Wako is identical to the definition of nearest neighbor search. So we leverage this fact and implement Wako search strategy using state-of-the-art NS library. Specifically, we treat sparsity pattern as a query, superschedule as a set of points, and our cost model as a distance function in nearest neighbor search. We evaluated Wako on multi-core CPU and tested on thousands of real-world matrices. And we prepared 4 baselines in different columns. 2 are based on auto-tuning approach, and other 2 are fixed implementation written by experts. We also test Wako on 4 different sparse tensor algebra kernels, as you can see in the different rows. As you could see, Wako outperforms all baselines on all 4 different sparse tensor algebra kernels on average. And it also shows good results on not only 2D sparsity pattern, but also 3D sparsity pattern like in MTT-KRP. To summarize, we made the search space to consider both format and schedule to allow co-optimization and explore this enormous search space with nearest neighbor search. We also designed Waconet that uses submanifold sparse convolution to avoid downsampling. And by using more stride layers, it can capture a pattern with distant non-zeros. And here are some final takeaways I want to share with you. First, there's no free lunch. Wako must pay search costs for the speed up. Wako is only beneficial for the application that has multiple repetitive runs on the same sparsity pattern. Second, when we analyzed the optimal format and schedule found by Wako, we found out that the load balancing was the most important factor in optimizing CPU performance. So without changing any format, by just changing the OpenMP load balancing parameter, you can get the really good speed up sometimes, in a lot of times. Third, increasing sparsity in dense block can improve performance, surprisingly. For example, if you see the sparsity pattern in the below, like the human or expert will choose the 2x2 dense block size because this seems natural. But Wako found that it turns out to be 4x4 dense block format was faster than 2x2 dense block, despite its increased sparsity. This was mainly because larger block size can enable vector instructions in your CPU, and even if we store more unnecessary zeros compared to those small blocks. Thank you for listening to my talk, and I'm happy to take any questions.